Thank you very much. Thank you very much for inviting me here, and also for the very kind invitation. Sorry, for the very kind introduction. Right. So yeah. So I'll be talking about this topic here: high frequency limits in general relativity, and for this problem, I'll be talking particularly about a conjecture that Burnett raised a few decades ago. So let's maybe start with the outline. So here's the plan, exactly as the title. I'll start with talking about the problem, what high frequency limits are, or what do I mean by this. And then I'll talk about the Burnett's conjecture. So I'll talk about what the conjecture is, some results. And then I finally want to end with some maybe applications of this conjecture. So I should first say that, of course, this is a conference about GR beyond vacuum. But actually, most of my focus will be about vacuum, so I hope that's okay. But then at some point, somehow, matter field will arise, even if I'm just thinking about vacuum. Okay? So let me start by thinking about high frequency limits. And in fact, I want to start by thinking about not GR yet, just the very general class of problems I want to understand about high frequency limits. And this is just general problems about PDEs. Okay, so I have, let's say, a second order, or you can ask actually even more generally, but let's say a second order PDE, so fixed something that's nonlinear. And the problem I want to ask is that suppose I have a sequence of solutions, and suppose this sequence of solutions converges to some limit. Okay, so now the question is the limit also a solution to the PDE? Of course, this way of asking the question is not really well formulated, because of course you will tell me that it depends on what I mean by convergence. And it's true that suppose I have convergence which is very strong, let's say in C2, then obviously the limit would also satisfy the PDE, because okay, this is second order, so every term converges, so it converges. But what would be more interesting if I ask that, well, the convergence would be in a weaker topology, and do I still have that the limit satisfies the PDE? So let's think of a couple of examples, so we have something more concrete to think about before we actually turn to thinking about this problem in general relativity. So let's fix the following setting. So let's for now, this is what I'm going to mean by convergence. So what convergence would mean is that I would have now a sequence of solutions phi n, and convergence means let's say uniformly, or well, everything is really local, so let's just say even locally uniformly on every compact set you have a uniform convergence. But now that's it. I really just want to ask for convergence without any derivative, and suppose I have some derivative of phi n. That I don't ask that it converges. I just require it to be bounded, or again, since everything's local, just bounded on any compact set. And of course, if it's bounded, then I know that it would have, well, at least after passing to a subsequence, that the weak limit, that would have a weak limit, it will converge to weakly to the derivative of phi n, but not the, sorry, the weak limit, right, of phi n, which is phi infinity, but this is not the strong limit. Okay. So now let's look at a couple of equations that you can ask this question. So the simplest sort of nonlinear PDE you can write down is perhaps this, just the Laplacian of phi equals derivative of phi squared. Okay. So now suppose I have a sequence of solutions, okay, which converges to some limit, and the first derivative is bounded. Now I claim that the limit would also satisfy the PDE. And it's not so difficult to see. The reason is that, well, I have this Laplacian, and Laplacian regularizes. So even though I only assume that I have uniform bounds of the first derivative, you can use the PDE to show, well, in fact, you have uniform bounds for every derivative. In particular, after passing to a subsequence, you have convergence actually in C2. And I've told you if you have convergence in C2, then the limit would be a solution. Okay. So using elliptic regularity, one can show that, in fact, the limit would be a solution. Okay. So the answer would completely change if I change the PDE, of course, if I change it to something like a wave equation. So instead of looking at Laplacian phi equals the derivative of phi squared, I look at the wave operator of phi equals dt phi squared, let's say. And now, well, I'll not show explicitly, but you can convince yourself that it's not very difficult to construct examples where you have a sequence of solutions which satisfy the assumptions I mentioned, sort of uniform convergence to a limit and uniform boundedness of the derivative. But then the limit actually is not a solution. And the issue here is that, of course, this term is exactly where the issue is, this term, where I only have weak limit. And of course, I know that weak limit and taking product do not commute. So the weak limit of the product and the product of the weak limit, they are different things. And therefore, at the limit, I get some defect, and the limit is not a solution anymore. But now another thing, sort of example to keep in mind, is that I can look at my wave equation example and sort of change the nonlinearity maybe just a little bit. It turns out that if I, instead of looking at just dt phi squared, but I look at dt phi squared minus dx phi squared, then there's a phenomenon which is very well known, known as compensated compactness. And for this one, can check that if I again have the similar assumptions as before, that phi n has a uniform limit and the derivative is only bounded, then in fact the limit would also be a solution. Okay, so let's just quickly try to convince you why this is the case and what actually is sort of the special dt phi squared minus dx phi squared doing. So one way to see this is you rewrite your nonlinearity as I did here, to rewrite it as -1/2 box of phi squared plus phi times box phi. Okay, so this you can only do because it's this special nonlinearity. You can rewrite it like that. Okay, so now what can you say? Of course, the first thing you want to say is you want to look at the first term, and you see that, well, you have this phi squared. Okay, I told you phi has uniform limit, so phi squared has uniform limit, so it converges strongly to the limit. But now, then it's acted on by a linear operator. Okay, and therefore, distributionally, of course, box of phi squared would converge to the limit box of phi squared. Okay, so then this actually converges to the correct limit distributionally, and therefore, okay, the limit is a weak solution of but if I can show also the second term has the same thing, I can say the limit is a weak solution. And why is the second term also good? Well, now notice the following. I can rewrite this as phi times box phi, right? So what can I say about phi? What I can say about phi is that it has a strong limit. Okay. What can I say about box phi? Well, box phi I cannot say it has a strong limit. I can use the equation to say that, well, box phi is equal to dt phi squared minus dx phi squared. Therefore, it's bounded. And therefore, after passing to a subsequence, I have a weak limit. Okay. So I don't know that I have a strong limit, but I know that I have a product of two things. One has a strong limit and one has a weak limit. And therefore, I know that, well, the weak limit of this product is the same as the product of the limits. And therefore, I can again pass to the limit. Okay. And because of this particular special structure, I know that I can pass everything to the limit with no defect. And therefore, the limit phi infinity would also be a solution. And this particular thing, of course, one can identify this as a null form, and it is a null form that has this special cancellation allowing us to pass everything to the limit and also get a solution. And now what we are going to do in the rest of this talk is exactly to try to do this kind of games, but for general relativity. So I want to ask this question in the context of general relativity. So let me introduce now the relevant PDEs that I'm interested in understanding, which of course is the Einstein's equation. So the setup, I'll only be thinking about 3 + 1 dimensional Lorentzian manifold here. And first, well, first thing that I want to study, in fact, for most of the talk, what I will be thinking about is the vacuum equation, right? So Ricci equals 0. And of course, okay, I can't come to a conference about sort of GR beyond the vacuum, just talking about the vacuum equation. So I'll have to tell you something about some matter. So I'll consider particularly two types of matter fields. They both have the property that the matter is null. So the matter propagates with the speed of light. So the first example is the Einstein null-dust system, where the Ricci curvature, I'll look at actually just this particular case of null-dust system, where the Ricci curvature is given by a sum of dust. Okay, so each dust has the property that it the stress energy momentum tensor looks like f squared du tensor du. And what property they have to satisfy? So first of all, the u has to satisfy that it's null. So the metric x on du is 0, and f just propagates with the transport equation along these null hypersurfaces with the transport equation that I've written down here. Okay, so this transport equation. Okay, so that's the Einstein null-dust system. I can have many families. So this can be an arbitrary, but maybe finite sum of different families of dust. Okay, so another matter model that I'll consider is the Einstein-massless Vlasov system. As I'll try to convince you in a moment, you can try to think of the Einstein-massless Vlasov system as the now dust system, but you take an infinite sign. Okay, so now you allow really propagating in all directions. And what is this? So you can write this down. So what this is you have a Vlasov field F, and the Vlasov field will satisfy a transport equation. Now the transport equation, you can write it down in terms of the Poisson bracket. So this is just this equation, the Poisson bracket with G inverse CC equals 0. I should say F is a function on the cotangent bundle, but it's supported on where things are null. Okay, so I have this function F, and it propagates with this transport equation, where the Poisson bracket is given by the formula in the last line. Okay, and now the Ricci curvature, it's just given by this F appropriately integrated with an appropriate volume form. Okay, so now what I'm going to try to understand is, in fact, I'm just trying to ask the kind of questions I've been asking about limit for general PDEs. Now I want to ask for the Einstein vacuum equations. And in this process, one will see the other matter model that comes up in trying to understand the high frequency limit. Okay, so let me be more and more precise. So here's the precise problem that I want to ask. So you can see there's some resemblance to what we were asking for general PDEs earlier. So this has a long history. Somehow this type of limit has been studied since Isaacson in the 60s, and then there are lots and lots of work, including some of the names I have put down here. Some of the names will reappear later in the talk. So now here's the precise question that I want to ask. So I want slightly more precise information than I had earlier. What I want to say is, well, G, I have a sequence of metric which satisfies the Einstein's equation. So Gn satisfies Einstein's equation Ricci Gn equals 0. And now I want to say, well, they converge in some coordinate system uniformly to some limit G infinity. Okay, but I want to say something more quantitative. So let's say I want to say Gn minus G infinity in L infinity, they converge. Let's say so they converge. So that means they are smaller than a sequence of number lambda n, which goes to 0. Okay. And now, well, like what I had before, I want to say that, well, the derivative, I don't require to converge. I only require the derivative to be bounded. Okay, so if I take the derivative, let's say here, k equals 1, then I only require this to be bounded by something order 1, so lambda n to 0. But I also want some information about higher derivative, but every higher derivative I take, I will allow myself to lose a power of n. So the second derivative, when they don't converge, it becomes very large, but I want some control. And the question is, what can I say about G infinity? In particular, does it still satisfy the PDE? Is it still vacuum? Okay. So this particular ansatz that you want to impose about Gn minus G infinity, well, you can think what this means is that you have convergence. So the amplitude becomes smaller and smaller. So it goes to 0, like lambda n, but the amplitude goes to 0 in a particular correlation with the frequency, right? Because every derivative against costs you lambda to the minus 1. So what you want to say is that, well, this convergence happens, well, the amplitude is smaller and smaller, but with like lambda n, but the frequency is like lambda n to the minus 1. So I want to understand what's the limit, and if it's not vacuum, let's say, then, well, it must be the case that I've write down the Einstein tensor. There's some right-hand side, right? There's some stress energy momentum tensor. I want to understand what happens there. What would be the effective matter that arises? Okay. So maybe it's good to start with an example. So here's an example that one can keep in mind. So let's try to construct a sequence of solutions which satisfies the Einstein vacuum equation. And I want to construct an example so that, well, satisfy all the previous assumptions, so that I have convergence, the first derivative is only bounded, etc. And I want to understand whether the limit would also satisfy the Einstein's equation. Okay. So now here's one way of easily generating solutions to the Einstein vacuum equation, which is to consider the so-called plane waves ansatz. Okay, so I would like to consider one parameter family of metrics parameterized by lambda. So look at G lambda here. So this is the form of the metric I've written down here. Okay, so minus 2 du dv plus h lambda. So this is one parameter family of functions depending only on v, not on u and y and z, squared, and then e to the g dy squared plus e to the minus g dz squared. And g, again, is a one parameter family of functions depending only on v. Okay. So why is this useful? This is useful because you can compute all the Ricci curvature, and you can check that, well, essentially all Ricci curvature is 0 except for one component. Okay. So in these coordinate system, the only non-trivial component is the VV component of Ricci, and you can write it down explicitly in terms of h and g. Okay. So it's this combination of derivatives. Okay. So now, well, one should maybe note that, of course, Minkowski is secretly sitting in here, where if you take h to be equals to 1, g to be equal to 0, you have Minkowski. But you can generate more general solutions to the Einstein vacuum equations just by the following procedure, right? So what I want to do is I just prescribe any g, okay? So I already know that all Ricci curvature components except for 1 is 0, so I just have to set this one to be 0. And this one I can, of course, set to 0 no matter what g you impose by solving an ODE in h. Okay, so I can solve it always locally, an ODE in h, and then I impose this Ricci to be 0, and then that's a vacuum solution. So let's do that. So what I want to do is I want exactly something that's very high frequency, right? Highly oscillatory, right? So that in particular, even the metric coefficient converges, the derivative doesn't. Okay, so this is exactly what can do the job, which is I look at g lambda, which goes to 0 as lambda goes to 0. So I have an amplitude lambda multiplied by some smooth function k, and multiplied by something that's highly oscillatory but with frequency 1 over lambda. Okay, so I have lambda kv sine v over lambda. So that's the g I want to impose. And then now I want to solve the Einstein vacuum equation. In other words, I want to solve the ODE in h, as I said. So I impose this ODE in h, okay, with some initial condition, doesn't really matter. Okay, so now I want to understand whether you have a limit. Okay, so let's think. I have to think about the limit of both g and h. So g obviously has a limit. And the limit is 0 because as lambda goes to 0, this is 0. Notice that only g goes to 0. The derivative is just bounded, right? It has an oscillatory term, and the derivative only converges to 0 weakly, not strongly. Okay. Now what about h? Now h, of course, solves this ODE. Now the point is that the limit of h will solve the ODE not with the limit of g squared, but it's with the limit of g squared. Okay, so you have to first take the square and then take the limit because the ODE only sees the square. Okay, so what's going to happen is that, well, g goes to 0, as I said, but what h does, well, h will go to the limit of g squared, and the limit of g squared, the weak limit, would exactly be this term. Okay, so now you have minus h double prime over h is equal to this square term. Now, if you compute the Ricci curvature, which is this, is the Ricci curvature of the limiting metric, it will be equal to this, and it's not 0. Okay, so this is exactly because taking weak limit and taking product do not commute. I generate a non-zero Ricci curvature at the limit. Okay, so another way to say this is that now I have a limit. G is equal to, again, of a plane wave form. I have a metric which looks like this, right? But now this is non-vacuum. Okay, so then matter can be generated at the limit. But in fact, if you think about this, this is a very, very special kind of matter, one that we have already encountered its definition, which is it is actually a null dust, right? Because this is Ricci equals to some amplitude here times dv dv. Now you can check that v is null because you go back to the metric form, right? There's this metric form tells you exactly that dv is null, and k is a function of v alone, or in other words, it's propagating with the transport equation like this, right? So k does not depend on the other variables, so it satisfies the transport equation. It depends only on v. It's transported. So this is a solution to the Einstein null dust system. So in particular, what you can see is that in these high frequency limit, you can generate matter which satisfies the Einstein null dust system. Okay. So now once we have one example, we want to understand sort of what can happen. What are all the possible examples? Can we, for instance, characterize the possible limiting matter? And here's where Burnett's conjecture came in. In this paper, the high frequency limit in general relativity, and here are the conjectures. Okay? So what he conjectured in this paper is, first of all, that any limit of vacuum solutions in the sense I mentioned above, uniform convergence, and the first derivative is only bounded with some control with second derivatives and so on. If you have a limit, then it must be isometric to some solution to Einstein-massless Vlasov system. So in other words, you must be able to find some Vlasov field so that you have a solution of, so that this metric is a solution to Einstein-massless Vlasov with that Vlasov field. Okay, so this is what he conjectured. And moreover, he also conjectured that not only all the limits must be Einstein-Vlasov, in fact, give me any solution to Einstein-Vlasov, it must be achievable as a limit of vacuum in the sense we described above. Okay, so this is what he conjectures that this is an exact characterization of high frequency limits. So here are his exact words. He said, well, if you have this T, which comes from a one parameter of metric satisfying the conditions 1 to 4, which is sort of related to what we have been discussing, then there must exist a scalar field, which is the Vlasov field, defined on the null cotangent bundle, so it's massless, such that the stress energy momentum tensor is given exactly by integrating this Vlasov field. And the Vlasov field satisfies the transport equation, right? And then a little bit later in the paper, he said, well, not exactly formulating as a conjecture, but he said, well, it would be interesting also to know if the converse of the above conjecture is true, that is to say, given any metric on a fixed manifold and a scalar field on the null cotangent bundle satisfying all these conditions, so that is to say you have solution to Einstein-massless Vlasov, then there exists a one parameter family of metrics satisfying the conditions of high frequency limits such that the limit is the given metric. If this is true, we do not need to impose any restrictions on what fields A and G we use other than, well, exactly the Vlasov equation. So what does this all mean? So what Burnett, before I explain that, I should say that, well, one thing that you would ask is, well, I gave you an example of such thing happening. And in that example, the limit is null dust. Okay, so better the conjecture, if it's consistent, it should also consist of null dust. And indeed it does. So the claim is that, well, in fact, you should think of null dust as a particular case of massless Vlasov, which is when this integral is a finite sum. So that is to say, this A is a sum of delta function, then you reduce to the null dust case. Okay, so what does this all mean? What Burnett says is, what this means is the following. So think of this A squared, this Vlasov field, as a particle distribution function on the null cotangent bundle. Then if the conjecture is true, we see that these particles do not interact directly, but they only affect one another by the effect on the background spacetime. Further, we then have a complete system for describing the effect of high frequency waves on the background spacetime. That is, on a fixed smooth manifold M, we have a metric G, and on the null cotangent bundle constructed from M, we have a scalar field A squared. The fields G and A squared then evolve together via this equation with T given by the Vlasov equation. So what this means is that, well, you can capture high frequency limit with Vlasov. And the property that they have is that they don't interact directly with each other. High frequency waves propagating in different directions. They don't directly interact. They only interact through the effect on the underlying geometry. Okay. So, well, this is just quickly to check that we are not crazy, that null dust is indeed a case of massless Vlasov. In order to do that, we need to define Vlasov in a way that allows for null dust, right? In order to prove anything about Vlasov, Burnett's conjecture. So let's quickly do that. So what I want to do is, instead of thinking about Vlasov as a particle density function f, I will have to think of it in a weak sense. So I want to introduce it in a measure value sense. So the way to do it is, well, instead of thinking of a function on the cotangent bundle, I would like to think of actually a measure. Okay, so let me just say how I want to think about it. So first I look at the the cotangent T star M. First, what I want to say is that well, all these things about high frequency things, I only care about the directions they are propagating. Okay, so it doesn't matter sort of how fast they are propagating because they're all propagating the speed of light. So the correct thing to think about is to look at the co-sphere bundle, which is to look at T star M, the cotangent bundle, but I introduce an equivalence relation, which is 2 points are equivalent. So xc is equivalent to x lambda c if lambda is some positive number. So if in the same direction, I identify this. And the measure I want to think about would be a measure on S star M. Okay, so I should think of course, this as a functional acting on continuous function on S star M. And it would be convenient to think of this as a functional acting on homogeneous functions on T star M. And okay, just to fix some notation, let's say homogeneous of order 2. Okay, so I'll from now on think of measures as something that acts on functions which are homogeneous in the C variable. Okay, so once you have this, then it's clear what I should think about the weak notion of Einstein-massless Vlasov is, which is I should think, well, the Einstein's equation holds weakly. So for any smooth vector field, x and y, I have this integral condition holds. I have this measure is supported on the now cone here, right, the second condition, so that everything is massless. And finally, I have the transport equation, but to be understood weakly. Okay, so instead of I have that acting on f, I would act on a test function. And for any test function, I integrate with respect to my d nu, I have this equals 0. Okay, so then if you define this, so one can check an easy lemma, which is suppose I have a solution to Einstein now thus. Then if you define the measure to be some appropriate delta measure, then this measure indeed is a solution to Einstein-massless Vlasov. Okay, so now we have set up the conjecture, right? So now we have set up the conjecture. Now we want to ask sort of what can we say, what can I prove about it? Can I, if I have a limit, can I always find a Vlasov measure so that I can identify the limit as a solution to Einstein-massless Vlasov? And conversely, if you give me a solution to Einstein-massless Vlasov, can I always find a sequence of vacuum solutions that achieves it? Okay. So the first thing that's known is the theorem of Green and Wald, which says the following, which is something that tried to say something about the limiting stress energy momentum tensor. So the theorem is, suppose you give me the setting as in Burnett's conjecture, as in this the assumption. So suppose you have some high frequency limit. Then the claim is that the limiting stress energy momentum tensor must have the following property. First, it is trace free. And second, if you pair it with any causal vector x, it's non-negative. Okay, so one should note immediately that if the Burnett conjecture is true, so that is to say, if T is identifiable with the stress energy momentum tensor of some Vlasov measure, then immediately you would know that it's trace free and it satisfies this weak energy condition. But of course, okay, the Burnett's conjecture is stronger, so that this characterization does not imply that you actually come from some Vlasov. Okay, so there's more one would like to think about. So now I want to tell you what can we say, some results that we can say. Okay, so I should maybe say that both of Burnett's conjecture, as stated, they are still open. Okay, so there are only some subcases that we can say something about. So the first thing I want to say something about is when you have a symmetry condition. And this is the U1 symmetry condition. That is to say, I want to think of my 3+1 dimensional spacetime having a translational symmetry. Okay, so here's the precise setup. The precise setup is, well, let's say I take some coordinates, x0, x1, x2, x3, and everything is symmetric in the x3 direction. Okay, so then I can write my 4-dimensional metric in the following form here. So I have a 2+1 dimensional part plus something that have the x3. You could have some cross terms, but importantly, the psi here and the g here and the math frac a here, they all do not depend on x3. Okay, so that only for now work in this setting because the full thing it's too hard. So I'll look at this setting, and then I also put in a further condition, which is I look at G, which I have the form of the following metric. Okay, so this you can always impose. Let's say if you're small data, you're local. And what's special about this metric? There's only one thing important, which is I have chosen such that if you look at t equals constant hypersurfaces, okay, so that's to say you look at the metric. So now you look at the induced metric. The induced metric, that's to say you look at only the dx part, and you have this dxi dxj, right? I want the induced metric on every t equals constant slice to be conformally flat. So it's some function multiplied by the flat metric. Okay, so this is a gauge condition that I can impose because I'm in 2+1 dimensions. Okay, and let me also impose that all the t equals constant hypersurface have zero mean curvature. Okay, so this is another gauge condition I want to impose. So now I want to just study the Burnett's conjecture under this assumption. So what do I gain here? Well, what I gain here is that I have a nice reduction of my PDE. So first, the Einstein's vacuum equations now reduces to a 2+1 dimensional system of equations. So this is a well-known reduction. And after this reduction, I would have a 2+1 dimensional Einstein's equation. So you see the Ricci equals to some field, and these fields, they satisfy a wave map equation. Okay, so so here's the system. And now I moreover impose, remember, the gauge condition that on every constant t slice, the metric is conformally flat. Well, what this means is that schematically, I would have the following system of PDE. So I have the wave map part, right, which is box psi equals to some quadratic function in derivative of phi. But then my gauge condition will also tell me that my metric component actually satisfies an elliptic equation, right? In fact, elliptic equation with the flat Laplacian, because my metric is conformally flat on each slice. So I have sort of schematically this system of coupled wave elliptic equation. And now once I've written down everything as a PDE, now I can really ask just a PDE question. So that's to say if phi n and gn, they converges in a particular way, as we mentioned before. So it converges like lambda n, as lambda goes to 0. If you take every derivative you take, you are allowed to lose the power of lambda n. Can we say anything about the limit? Okay. So here's the first result. This is joined with Cecile Huneau. And the result is under the conditions above, the conjecture is true. So that is to say, you would have you have this limit, and this limit actually corresponds to some Vlasov. So you can find the Vlasov measure such that there is a solution to Einstein-massless Vlasov with this measure, and this metric would be isometric to your limit. Okay, so let me just quickly say sort of the punchline here. I'll try to tell you a little bit about the proof in a minute. The punchline here is that well, there is, so if you think back to sort of the very beginning of the discussion, this is about whether we can pass the limit, where there's compactness, right? And the punchline here is that, well, of course there's non-compactness because the limit is not vacuum. So you don't have things like compensated compactness fully, because that doesn't happen. You have something that's not vacuum. On the other hand, there is secretly some compensated compactness, because secretly, well, even though you cannot pass the limit has to take a very particular form. And in proving that statement, one sees that, well, in fact, there is some interesting cancellation that's happening, allowing you to say that, well, in fact, the limit also satisfies the Vlasov equation. So, okay, maybe I can have time to say a word. So let me just quickly try to convince you, or try to maybe give you some ideas of how to think about this problem. So remember, somehow the reduction with the symmetry and gauge condition is so that I have a reduction of this coupled wave elliptic system, like of this form, okay? And the two things that are important here, one is that Q is now a null form, right? Remember from the very beginning of the discussion that null form is something that has to do with compensated compactness, so it's useful for passing to limit. And secondly, this G obeys an elliptic equation, right, or a system of elliptic equations. And again, remember from the discussion early on that elliptic equations allow you to gain regularity, and that allows you to pass the limit. So indeed, that's the first thing you want to do. The first thing you want to do is just really compensated compactness, as discussed in the beginning of the talk, you want to just pass the limit for whatever you think compensated compactness is at work. So if you have null form, you pass the limit. If you have the G, you pass the limit because that you gain derivative, so that you can pass the limit. So the only thing that doesn't go to the limit is this final term that's in the equation for G, right? Because this is a phi, so that this does not satisfy a elliptic equation, and this does not have a null form. It just goes into the G equation, okay? But now you can identify this as the only issue, okay? So you know that, well, there has to be something that doesn't go to zero because you want to generate a Vlasov field. So, but you identify it's exactly this. And I now want to understand this guy. I want to understand this. I want to say this thing actually satisfies the Vlasov equation. So here is now how a measure comes in. The measure comes in by, you can introduce what's known as a microlocal defect measure, introduced independently by Girard and Tatar in the very early 90s. So this is just the following thing. So this is an object where I want to identify, if I have something that does not converge strongly in L2, I want to identify the issue, okay? So there are sort of two kinds of issues I want to identify. I want to identify first where the failure of convergence happens. And second, I want to understand in what frequency direction does this happen. So this can be very nicely captured by just considering the following. So look at, right, so you want to say you have something that converges, like psi n converges uniformly, but derivative is only bounded, so only has weak convergence. So you look at this psi n minus psi infinity. Okay, so if you look at the L2 norm, it doesn't converge. But I don't just think about the L2 norm. I first act on it by a Fourier multiplier, and then act on it by a spatial function. And I want to pass the limit. And the claim is that there exists a measure, right? So that you capture the subsequential limit. And the limit is exactly given by you integrating the B and the M with this measure. Okay. So now there's something very well known about microlocal defect measure, which is suppose you try to understand what happened with the microlocal defect measure for linear wave equations, just linear wave equation with a fixed metric. And the claim is that, well, you know that wave equations via this microlocal defect measure, it's well known that it corresponds to massless Vlasov. Okay, so this you can just show by some energy identities. And this is where sort of the connection comes in, right? So the connection comes in, we start with some wave-like things, and then I look at the microlocal defect measure, and then, well, I know that Vlasov comes in. Now, the only issue here, or the main issue here, is that, well, we are not thinking about linear wave equation. We are thinking about quasi-linear setting. So in particular, well, first of all, my wave equation is not just wave equation, it's wave map. I have a right-hand side. And secondly, I also have a metric, which also depends on the wave, right, via the coupled system. So I have to understand whether I will still be able to show that the solution at the limit corresponds to Vlasov under all this nonlinearity. And it's easy to convince yourself that in general, this doesn't happen. And if it does happen, it requires some special structure and cancellation. Okay, and this is exactly the, yes.
Can I just ask a question? Yeah, these microlocal defect measures, I mean, yes. If you put, are they somehow related to these Wigner measures, which pop up more or less at the same time?
Yeah, it's related. Yes.
Okay.
Yeah.
Okay.
Yeah. Okay, we can say some more maybe. Yeah, but it is right. So right. Yeah, okay. Let me just say so much for the moment. Right. So now here's the point here. So the point here is that the nonlinear terms, both actually terms from the wave map part and from the coupling with G, actually there is a form of trilinear compensated compactness. So let me just very roughly give you an example here. The example here is that, well, this again has to do with the null forms. And the point is that suppose you have some sequence of functions which are almost solutions to wave equations. So it has some wave property and you have a null form. Then the claim is, well, suppose you want to understand a trilinear limit of a weak limit of involving this, but involving this, involving this C, but in particular involving a null form, then if you even try to compute a trilinear thing here, then what you can say is that, well, you can pass the limit up to something that's at worst bilinear. Okay, and things which are bilinear you can understand using the microlocal defect measure. Okay, so let me just say this much, sort of just to give you a sense of how sort of the Vlasov measure comes in. Okay, so now this is one direction of the Burnett conjecture, of course. The Burnett conjecture also has the other direction, which asks, if you give me an example, can you find a sequence which achieves the limit? So we haven't had the result which sort of do this in this full generality, but there's a result here again with Huneau, which says that suppose you give me a generic small data smooth U1 symmetric still, but even more symmetric, let's say polarized U1 symmetric solution, but now not to the general Vlasov equation yet, but just a dust equation, so a special kind of Vlasov. Okay, then what we can say is that we can find a sequence of vacuum solutions. We can't say exactly that we have all the convergence that we want, like Burnett, but we have some convergence. But the easiest to state is that at least certainly we have the C0 limit is the given solution to the Einstein null dust system. Okay, so there's so this of course is very different from the kinds of problems that I've been telling you earlier, right? Which is much softer and you try to understand the limit. Here we have to construct something, right? We have to use the given solution to construct some highly oscillatory solution to the vacuum problem and try to understand the limit. Okay, so let me just remark that, of course, well, this is a special case of Vlasov. Namely, it's a special case that involves the measure is the finite sum of delta measures, right? As I told you, this is what the null dust means. But of course, we know that finite sums of delta measures are sort of are dense in the set of all measures in the weak star topology. So what one can hope is that, well, you start with this, just the dust, and you can try to pass to the limit of taking sort of more and more deltas and try to construct more general limiting solution to Einstein-massless Vlasov system. So this sort of we are working on this, but okay, I have nothing more to say at the moment. All right, so now let me shift gears to try to tell you another class of results, which doesn't require symmetry, but it requires something else that's different. But before we get there, let's somehow philosophize a little bit, sort of why the Burnett conjecture is interesting or it's difficult. And the real issue here is that whenever you try to think about this, including sort of the results I was presenting to you in the previous section in U1 symmetric case, is that this is, once you try to think about this, this is a low regularity problem, right? So for instance, if you try to construct examples of things whose limit is some given Vlasov solution, then you necessarily have to think about things which are low regularity. Well, for the reason that if we had uniform bounds in some H epsilon space, sorry, so I haven't said carefully what this is. So maybe, okay, so this is, okay, let's say H1, sorry. So the correct thing should be H1 plus epsilon for the metric. Okay, so suppose we have any sort of uniform bounds like that. The claim is then you can easily show that the limit must be vacuum. So anything that's interesting must happen actually at the first derivative of G, as you see, right? Because the first derivative of G should only be bounded and only has a weak limit. If you have anything stronger, then there's nothing interesting in the limit. And of course, we know that if you look at the Einstein's equation as a mathematical problem, try to solve the initial value problem, you do not have any results sort of about low regularity in such low, about well-postedness in such low regularity. Okay. And therefore, we have to look at sort of, right, precisely in the previous section, we have to look at sort of special cases. We have to look at sort of special constructions with null dust in order to think about Burnett's conjecture. But now here is another sort of setting where one can think about where one can think about Burnett's conjecture. Precisely, there's a special setup where we can actually understand well-postedness in a low regularity setting, which is consistent with the metric only being in H1 and no better. Okay, so this is a result with Igor Rodnianski in 2013. What we show is the following. So of course, I just told you, in general, I cannot expect the local well-postedness result at the low regularity with only one derivative of the metric. So that's too low. We don't know anything. However, we consider the following setup, which is we look at initial data, let's say on two intersecting null hypersurfaces. Okay, so I have two null hypersurfaces, and I put my data, characteristic data on these two null hypersurfaces. And on these null hypersurfaces, I foliate. So these are all, let's say, spheres. And on each of these, I foliate with spheres. And what I want to say is I have two directions, let's say u bar and u. And I don't require anything more than the derivative of the metric to be in L2 in the u and u bar direction. However, what I require is that on the angular direction, I have more derivative. Let's say, I don't know, 10 derivative. Okay. And this is a class for which we can actually have well-postedness. So that is to say, you can give me data, which is only W12 if you measure in the worst direction, but it's better in the better direction. Then one can still show that there is a local solution, and the region of existence only depends on the norms that I discussed. Okay, so the W12 norm with higher regularity in the spherical direction. But this is exactly now a setting for which we can try to understand the Burnett's conjecture, right? Because now we have a well-postedness result in the regularity level that's consistent with just one derivative in L2, no better. Okay, so you can ask, suppose I have a sequence of space-time, in fact, a sequence of data satisfying the assumption of this theorem. Can I say anything? Can I pass the limit, right? Because now I already know, just look at data. I can have a solution. I have a well-postedness theory. So now we can use that. And in fact, one can completely classify the limit in this setup. What one can say is you can give me a sequence of data satisfying the estimates from the previous theorem uniformly. Okay. So the theorem, of course, then tells me that there's a region of existence depending only on the norms. Okay. And now the claim is that, well, you can find a subsequence so that the subsequence converges to a solution to the Einstein-massless system. Okay. So now I can completely classify the possible limit. And because of the extra angular regularity that I impose, only now-thus can happen here, because I can only oscillate in two directions. So I can't oscillate in all directions, so I don't get general Vlasov. And moreover, in this setup, because we have a well-postedness theory, in fact, what we can also say is that suppose you have a solution to the Einstein-massless system, which has a similar property, which I call angularly regular. That is to say, I only have one derivative in the bad directions, but regular in the angular direction. If I have a solution to the Einstein-massless, then in fact you can always achieve it as a limit of Einstein vacuum, exactly by doing the following. Exactly by trying to approximate the initial data, right, in this no norm, and then try to solve using the existence result, the low regularity existence result, and then and then you can pass to the limit. Okay. So I have maybe 8 minutes. Okay, maybe let me try to say one application of all this, and then I'll finish. So I'll skip part 6, I think. Okay. So right. So now, up to now, right. This is all about sort of Burnett conjecture itself. I'm trying to understand this link between high frequency limit of vacuum things and, let's say, now dust and massless Vlasov solution, where it turns out that this also can help us to try to understand something in vacuum. So here's one example I want to discuss. So the beginning of the story is the so-called null-dust solutions. So what are these? So the first null-dust shell solutions, null-dust shell solutions. The first one was discovered by Sink quite a while ago in 1957, which is the following solution to the Einstein's equation, which is You can write it down explicitly. Yeah, you can also think pictorially. So it's the following. Okay. So what he found is a solution where, well, okay, this is Minkowski. Okay, so that's not surprising. Now, then what he then found is that he can paste Minkowski to Schwarzschild. Okay, so that's what he did. That's all. Okay. But then, well, of course, you can't just paste because the junction is not, there's a problem in the junction. And indeed, there's a problem in the junction. And the junction is a null hypersurface. And at this junction, what you see is that it's not vacuum. So you want to have a vacuum solution, but at the junction, you don't have something vacuum anymore. Okay, but what is it? So what he found is that at this junction, in fact, it looks like you have a delta function of null dust propagating. Okay, so this is the delta function. So this is a null dust. But this null dust is just a delta function, right, on a hypersurface, on a null hypersurface, and that's why it's called a shell. So it's a shell of null dust that's propagating. Okay, so this is a particular example, but then starting from that, there are many other examples. You can look at other dust, you can interact them, you can look at two and cross them, and so on. And one question one can ask is, can I try to understand this more generally? Can I try to have a general local existence result for dust? So now here's one way to approach this problem. Well, which is try to use the correspondence between null dust and vacuum things, okay? Through the Burnett conjecture. So here's the result. So the theorem is that you can consider the characteristic initial value problem now with Einstein null dust. So again, this problem here like this. But now I have some dust. So I have some dust initially, some dust initially. Initially, they're delta function, and I want to propagate them, right? So I want to say they propagate, and then I have two null dust shells that interact with each other. Okay. So I have, well, the data. And indeed, the theorem says that, well, you can solve the Einstein's equation, and you will have two dust that interact as I just drawn to you before. Okay. So what does this have to do with Burnett? So perhaps this can explain. So the way that we prove this in particular also show that any null dust shell solutions, including those we construct in the theorem above, actually arise as a limit of smooth solutions to Einstein vacuum equations. Okay. So in fact, this gives you a way to construct null dust shells just by understanding vacuum well. So one doesn't have to do it directly for null dust. So what this means is that, well, we would, right, so how does the proof work? The proof goes through, you use the rough data existence result that I described previously for the vacuum equations. And then I take limits. And when I take limit, I would get a null dust. Okay. And notice that there's one thing that's different from the previous thing that I was discussing. Here, I'm not looking at high frequency oscillation. I'm looking at things getting to a delta functions. So this is a concentration phenomenon. And it turns out that you can also use this type of ideas to understand concentration, not just oscillation. Okay. So let me finally end with an amusing another application of this this fact that you can construct null dust shells out of vacuum things. So I've told you this example of zinc, right, which you paste a Minkowski to a Schwarzschild. Of course, that's an example of a propagating null shell, but it's certainly more than that. It's an example of you form a black hole, right? You start with Minkowski, some completely flat, and then you send in some matter field. And after you send in matter field, what happens is that, well, you have a black hole, right? This is Schwarzschild. So you have a black hole formation by the null shell. Of course, this is a well-known problem, and this was a very hard problem for the vacuum. In null dust, okay, you can write it down directly. Zinc already wrote it down, so it's much easier with matter with null dust. But in vacuum, this was a hard problem, which was, of course, finally solved by Christodoulou in 2008, which says that, well, you can actually form a black hole or form a trap surface without matter just by focusing off gravitational waves. Okay. But let's think a little bit about how Christodoulou did this problem. So he did this problem by what he called the short pulse method. So here's the picture that I borrowed. So the way that he thought about this problem is the following. So he wants to send in gravitational waves from far away, right? And of course, it's very difficult to control the space-time if you just consider something very large. So he introduced a smallness in the problem, which is the length scale. So he wants to send in gravitational waves, which are concentrated on the length scale of size delta, let's say. Okay, so he sends in this, and because of this small length scale, he can understand the space-time sufficiently well to show that finally, at some point, you form a trap surface. Okay, and then you can say, well, by Penrose's theorem, therefore, something bad must happen, including incompleteness and so on. Okay, so now, well, the natural question you can try to ask is that, well, you have a delta here. What happens if I send delta to 0? Right? If I send delta to 0, what do I get? And what we can show is that if you send delta to 0, what you get is exactly a null shell. Okay, so in fact, the kind of data that Christodoulou considered, if you send the delta to 0, the scaling is such that you would have some matter, and the matter is exactly the null shell, like the sinc solution, for which we know that you can form a trap surface. Now, so here is another way to think about this. Of course, this is not the way that history happened, but another way to think about this is the following. So we all know about sinc solutions from the 50s, and now we all want to think about the vacuum problem. We want to understand whether trap surface can form in vacuum. So suppose we don't know this work of Christodoulou, which of course we do, but let's suppose we don't know. We can try to do the following thing, which is I'd start with the sinc solution. And suppose I know about all these things about Burnett. I know that, well, now dust has something to do with vacuum. So then what I want to do is I want to approximate the sinc solution by vacuum solution, right? Because it would I can find vacuum, so it limits to sinc. So I find a vacuum solution that approximates this. And what we would have done if we have done this process is that we would have constructed what Christodoulou constructed. And that will show the formation of trap surface. So what this suggests is, okay, I'm not going to get into that, is that, of course, a lot of times, okay, there are many problems which are easier. In fact, if you introduce matter for various reasons, for instance, you can introduce symmetry, so the problem simplifies. Then it's easier than the vacuum problem. But let's say we ultimately want to understand the vacuum problem. So it's useful even, I mean, of course, there's reason to understand matter because, okay, matter arises. But even if I'm just interested in understanding a vacuum, it would be interesting to try to think about, let's say, a corresponding Vlasov problem, which often is easier in certain settings. And okay, then one can try to solve that problem and try to use this correspondence to see whether one can say something about vacuum. Okay, so that's the final thing I want to say. So let me just end here. Thank you very much.
Many thanks for that talk, Jonathan. Is there any question? Helmut, you have to unmute yourself.
Emphasize that you are not crazy. Nevertheless, I want to ask you a crazy question. You can convert vacuum into dust. I mean, I'm not surprised by this. Doing home office, I see this every day. But, what I'm asking is, can you convert some other matter fields into some other matter fields? Not that's but matter to matter.
Yeah, that's an interesting problem. Yeah, so I don't have answers, so I don't know. So actually, I think in Burnett's original paper, he also considered the case of Maxwell. So you start with Einstein-Maxwell, and you can try to understand what happens in the limit. I don't remember actually whether he formulated a conjecture there or not. But it would be interesting, for instance, to understand, okay, in that case, for instance, would you be able to get some charged dust?